All right, screen sharing. Where is that? All right. Wait a couple more minutes. Let me do some more making your lives miserable. So we need to go ahead and put up the project. Guess it should go on this level. Oh, fuck it. Oh, that's recorded. I'm the super laziest person in the history of the world. We'll get to it this way. Go to the home page. All these people in. Projects. Okay, let's all the 5-minute late folks. There, that should let people come and interrupt without me having to interact with them. All right, well, good morning, everybody, and let's see, make sure the recorder's on. It is. Good morning, everyone. Welcome to Computational Thinking and Data Science, our 19th meeting together, not counting the other 19 that are the labs. So we made it to November. Today is an important day. You should vote twice if you can, 3 or 4 times, however many they allow you to. By law, it's only supposed to be once. And I think if you vote twice, they throw them both out. Good job, Rame. 10 times already. So maybe they'll keep one of them, especially if you used a different name each time. So the topic for today is unfindable. Let's go to the home page. And we'll discuss the projects a little bit in the lab. There's more of that coming up, but well, we'll get to it when we get to it. So in our lesson collection, the topic is regression. And you might ask, what's that? And it's, if you watch enough Planet of the Apes episodes, you know what regression is. And it's an approach to data modeling. So we've been kind of sneaky all along. When we did the probability estimation modeling earlier, and you put red lines through blue dots, we were doing that with the intent to make this part a whole lot easier for us, not you. So if we look at the formal regression presentation, I'll go look through that quickly because it does mention correlation, which you'll see in your lab today. So it talks about association, correlation, coefficient, and regression. So the lab notebook I'm going to go through is mostly, is actually all regression, but let's look at what a correlation coefficient is. And you're supposed to be able to compute correlation using pandas. You'll learn that in the lab, and plot regression line of two variables. We'll see that, but I'm actually going to show you ways to do some different things. So what's meant by association? If we were to have two variables, perhaps acceleration and MSRP, manufacturer's suggested retail price. Okay, I get that. Those are seemingly completely unrelated things, right? How much something costs and how fast it accelerates. There's no expectation for them to have any association with one another. But when we plot that, we see this cloud of markers that's kind of moving up and towards the right. And if you have a high acceleration, your average manufacturer suggested retail price is much different than the average at a low acceleration. So that's an example of positive association. An example of negative association is shown here on the figure on the right, where everything is starting in the upper left and working its way to the lower right. This one actually, to me, it looks like there's curvature in it. In this case, miles per gallon is being associated with manufacturer's suggested retail price, and the more expensive thing has lower miles per gallon than the cheap thing, which has the highest one. Although if you look at those prices, if those are dollars, those are already pretty pricey things. My first car was nowhere near $20,000. It was more like $300, and that was when it worked. We've seen z-scores already.
Hello.
We're going to learn about correlation coefficients later on, which is the ratio of the products of the two variables expressed in some standardized units. I'm gonna have to mutate whoever is making noise. You are all mutated. I hope that didn't hurt too much. And I'm going to skip these examples. Let's see. Correlation only measures association. And in many cases, correlations are extremely misleading. We've given you examples of that before. Another related concept is called a regression line. And the correlation coefficient is sometimes useful for identifying a straight line around which the markers cluster. And here is the correlation coefficient based on the estimate of y minus the average of y over standard deviation. When we go through this, we'll come up with, frankly, I think a better way to get regression lines. And so here's what our end result is. The regression line in this case is the yellow line. The blue markers are the original data, and it looks like they have a little red prediction tool in here. So that's what we're headed for today. Go away, PowerPoint. There's some notebooks there that you can look at on your own if you wish. So let's go to our lesson. So ours is going to be lesson 19. That's the one I want to go through. And actually you can see an interesting one. That's not me. That's Farang's awesome animation there. Oh, and now it's not going to work. Okay. Lesson 19. Okay, so hopefully everybody's ready, especially since Rami already knows regression, so he claims he'll have no problem. But for those of you that don't, let's go. Let's close these things down. That's just to get my notebook to work the way I want it to. Okay, so data modeling, the regression approach. We've already seen data modeling when we used probability distribution functions as models of data. And here we're doing fundamentally exactly the same thing. And regression is a basic and commonly used type of predictive tool. And the overall idea is to assess a few things. One of the questions we use is to ask whether a set of predictor variables does a good job at predicting an outcome. And the predictor variables go by the name predictor, independent, explanatory, and actually the modern terminology is features because computer people had to get involved and wreck it for the rest of us. Any of you computer people, don't take that as too much of a slight. And then do a good job of predicting an outcome. Other words for outcome are dependent variable, response variable, and that's about it. And so that's one of the questions we address. Second one is which explanatory variables in particular are significant predictors of the outcome variable. We won't get to that today, but that's a way of, if you have multiple explanatory variables, finding those that are most useful in making your predictions. And in what way do they make those predictions and impact the outcome? And then the next important question is what's the estimated value of the response under various explanatory conditions? The whole point of doing this is to be able to predict something we haven't seen yet. And lastly, we want to address what the uncertainty involved in the prediction is. And when we get to that, you will find the interval estimates you've done already somewhat reminiscent. So the regression estimates are used to explain the relationship between one dependent variable and one or more independent variables. That's the usual approach. The simplest form is linear regression. That's what we're going to deal with today, where there's one response variable, and we'll start with one explanatory variable. Then I'll show you at the end of the lesson how to add more than one. There's certain conditions that have to be satisfied. So we're going to start with y equals beta 0, the intercept, plus beta 1, the slope, times x, where x is the predictor variable, or the independent variable, or the explanatory variable, or the explanatory feature. And so x is multiplied by this parameter beta 1, and then the value beta 0 is added to it, and that gives us an estimate of y. So here we're using y as the estimated variable. Beta 0 and beta 1 are two regression coefficients, and x is the independent variable. Normally we'll have multiple values of x sub I, maybe 8 or 10 observations, 8 or 10 observations of y. And one of our challenges is to figure out what beta 0 and beta 1 to use. Hopefully we'll get through purpose, background, and so forth. And we'll get to this for sure today, making regression models using primitive Python and creating linear regression models from NumPy. I don't actually have that prepared yet, so I might do that live. That should be fun for no one. And presentation quality graphs, that's actually already built into it. So in terms of computational thinking, so the computational thinking concepts that are involved in regression are the linear model itself, although it doesn't have to be linear, the data model itself. That's the abstraction step in computational thinking. The response and explanatory variables are a type of decomposition of that abstraction. So we decompose the model into a collection of things that we think are responses and things that we think explain those responses. Even in numerical stuff, we can even do cook and look stuff where we don't actually know, we just start plotting stuff willy-nilly. That's what that a Sanborn plot that we did earlier in, I think that was lab 9 or 10, somewhere back there. Then the arrays are a data representation, and then NumPy vectors and matrices are a data representation. So those are our computational thinking aspects. So what is regression used for, and why is it useful? Okay, so this chat is starting to annoy me. Let me see. The directory takes us to lab 19. Oh, I must have screwed something up. I'll deal with that later. It's not that important. I guess it is, but not right now. So a couple of fundamental questions. What is regression used for, and why is it useful? Literally, that's the only point of this section. The three major uses are determining the strength of predictors, forecasting an effect, and I guess forecasting a trend. So 2 and 3 are actually the same thing, forecasting, and then 1 is determining how valuable or non-valuable a predictor variable is. So for instance, the regression might be used to identify the strength of the effect that an independent variable has on a dependent variable. Typical questions are, what is the strength of relationship between dose and effect, sales and marketing spending, age and income, and so forth. So that's one of the uses of regression. If we're manufacturing therapeutical medications, we want to know what the dosage is to produce a desired effect. If the dosage isn't large enough, the effect isn't desirable, and the people might not come back for more medicine before they croak. If the dose is too big, they might croak before they have a chance to buy more. But if we get it right in the sweet spot, right at the peak of the poison curve, that's perfect. That's how you actually operate a bar. Is you want to get your dose and effect just right, because then your sales and marketing spending become negligible because they'll spend the money for you. Secondly, regression's used to forecast effects or impact of changes. So that's a pretty important use in engineering. The first one is also. And regression helps us understand how much the dependent variable changes with a change in one or more independent variables. A typical question would be, how much additional sales income do I get for each $1,000 spent on marketing? How much additional votes do I get for each $1,000 spent on hot dogs given to prospective voters? Those kind of questions are something that regression is useful for. And I picked that because today is voting day. Third, regression analysis can predict trends in future things. It can be used to get point estimates. A typical question might be, what's the price of gold in 6 months? Okay, so those are all business examples, namely because that was the easiest place to steal it from, where the language wasn't completely befuffering. I want to take you to 1977 to a page in TI-55 user manual. You know, y'all might do better on those exams if you just listen to me when I talk instead of messing around in the chat room. Okay, so there was Daddy right there telling you to pay attention. So here's the 1977 user manual, page 40, and in the TI-55 calculator, many of which were built before many of you were birthed. It was one of the early calculators that had statistical functions built into it. And a statistical function to an end user was a yellow button. I think I got mine here, I can't find it. I got it on my desk somewhere. But they have an example of using the yellow buttons to help produce predictions of data. Now the calculator didn't draw this graph. Graphing calculators weren't going to happen for another 20 years. But it would produce the slope and intercept that you could then draw the graph on a piece of paper. So let's read this. In many disciplines, it's desirable to express one variable in terms of another, even though the variables are independent and are not necessarily analytical functions of each other. An accepted practice is to perform a least squares regression, which is designed to minimize the sum of the squares of the deviations of the actual data points from the straight line of best fit. In practice, we are essentially constructing a plot of the variables called a scatter diagram and drawing the best straight line, which uniformly divides the data points as shown below. Because the data may not be best represented by a straight line curve, it's desirable to measure how well the linear curve actually fits the data. This measure is called the correlation coefficient and may be calculated from the independent variables in the linear equation parameters. So in the context of our class, this straight line right here, where the cursor is moving left and right, up and down, is the data model. The equation of that line is y equals beta 0 plus beta 1x. As of right now, we don't know what beta 0 and beta 1 are. The ordered pairs, xi, yi, are the markers, the little dots. So one of them here is labeled xi, yi. And it's depicted here, y is the response to different values of x. So by convention, not always the case, the up-down axis is where the response is plotted, and the left-right axis is where the explanatory or the predictor is plotted. Once you get to higher dimensional cases, those kind of plots are sort of hard to make. Doing two x's and a y, that's still doable with a contouring plot, but after that, there's no easy graphical way to do it. The model parameters, beta 0 and beta 1, once we know them, they allow us to estimate or predict response to any unobserved value of x. So the classical ways of recovering beta 0 and beta 1 are something called the normal, why did it do that? Normal equations, and I have them listed here. And it says beta 1 is the sum of the x's. Now these are observations. The sum of the x's times the sum of the y's minus n, that's how many observations there are, times the sum of the product xy, divided by the sum of the x's quantity squared minus n times the sum of x squareds. That gives us beta 1. And then beta 0 is the mean value of y, the mean of the sample y, minus beta 1 times the mean of sample x. So the equations themselves are pretty straightforward to implement. Where they come from, as of right now, they just came from the gods of data, but I'll show a somewhat of a derivation shortly. So let's actually just use the actual problem from the TI-55 user manual. What we can do that the user manual can't is we can go ahead and make a plotting package. And so we return to our lab 9 notebook, make some modifications, and we have a plotting package that I named Make a Bear. I have no idea what I was thinking at the time. And this one takes a list of x values, y values, and then it's going to also let us provide x left, x right, y right, and it'll draw a straight line through those 2 points, and we can have labels and titles, and it even tells us what things are supposed to be: floats, strings. This should probably say it's a list. And then we'll import matplot library, and then make a scatter plot, make a line plot with double dash lines, put our labels on it, a title, and then show the plot. Okay, so here are the numbers that were in the Texas Instrument user manual. In the Texas Instruments manual, they were predicting sample length based on sample weight of something. So these lengths are probably in centimeters. So, you know, something that's 101 centimeters long weighs 609 grams and so forth. And why you would use weight to estimate length is a different story, but let's suppose that that is somehow important. So here we're going to make the two lists. Good old-fashioned Python that we did weeks ago. Then we're going to send those lists to our make-a-bear plot. We'll plot sample weight and sample length. That'll be our scatter plot. We're also going to draw a line through the points 580, 96, and 630, 106 as a dashed line. And then there's some labels right here. So let's go ahead and run that. Save it. That's what I was afraid of. I think it's going to fail when I try to run it because there we go. Okay, I'm back in control. So let's go ahead and load in our plotting package. Nothing very interesting happens there. And we'll make our two lists. And let's look at our plot. So here we have 1, 2, 3, 4, 5, 6 blue markers in a dashed line. And all we did to get the dashed line is we provided two XY values. And you could look at that and say that that line looks pretty good. You got 3 markers above here, 3 markers below the line here. The line kind of passes nicely through every point. It seems like it'd be an okay predictor. If I went to 620, I would expect a length of about 104, which might be a little on the high side compared to this single point out here, but we're not ballpark goofy. Let's go ahead and see if we can, hope this will work. Want to be consistent with our, see what happens if I do that. Oh, sweet. Okay, so now we have our color scheme that we're familiar with. The red dashed line and the blue markers. So let me go ahead and ask everybody, you can either answer in the chat box or you can unmute yourself. In that plot, what is displaying the observations?
Blue dots.
Excellent. In that plot, what's displaying our model of the data?
The red
line.
Good, good. Okay, so in our dashed line, we only supplied dashed. Yeah, that's the one time spell check doesn't kick in. It's when it makes you look like a stand-up comedian. So we only supplied 2 pairs to plot the line. Oh, I didn't know I left this. So let's get a colonoscope and find out where it came from. Can you tell what time of day I might have typed this? Yeah. Rame, you'll know what one of those instruments is someday, about when you turn 50. Okay, so let's create a function. And what this function is going to do is we supply it with a slope and an intercept and 2 values. and it's going to return those two values and the y coordinates that go with that value. So that's sort of our linear model. And this may not have been the smartest way to do it, but that's what happened. So here's the myline function, and it's going to return a tuple, list x and list I, and then we'll have to access the tuple. So let's suppose we put it in with a slope of 0.1 and an intercept of 10. And again, we'll go from 580 to 630. Let's see what's going to happen to our red line when I do it. So the object is going to be the myline tuple, and then we'll pull the parts off the object and put them here into our plotting function. Right there. And there's nothing to have stopped me from typing object square bracket 0 spare bracket 0 right here, object square bracket 1 square bracket 0, except that there'd be no way in heck you guys watching it on TV would be able to make sense. So the object comes out of the myline function. Turns out the object is a tuple, so we actually have to pull the pieces out. Fortunately, it's a small tuple. It only has 4 things in it. X1 is position 0, 0. X2 is position 0, 1. Y1 is position 1, 0. Y2 is position 1, 1. And we'll put the X1, Y1, X2, Y2 here, and it will draw a line. So let's go ahead and draw that line. And we get an error. What is my error? Oh. Okay, so there it is. We haven't changed the data. The blue dots are still blue dots. The red line is nowhere close to the blue dots. What have we done? Unmute yourself. What did we do wrong? Trick question. We've done nothing wrong. It's just our choice of slope and intercept is pretty terrible. Let's try a 1 here and see what happens. I'd say that gets even worse. Let's try a -1. Sloping downward, also even worse. Let's try an intercept of 100 with -1. Still terrible. Let's try an intercept of 600 with -1. We're not getting anywhere. And fortunately, I left notes to myself. Let's suppose we did 0.1 and 20. 0.15 and 20. Ah, okay, so we're getting close. So now all we have to do is mess with the intercept. And I'm going to cheat. And there we are by trial and error. 0.13 and 23 produces this red dashed line, which is at least close to the blue dots. So is that our best line we can do?
Probably not.
Probably not. Let's see what happens if we drop the intercept by 1. Oh, what is it, Kat? You gonna actually join us today, or you just want to talk? We dropped the intercept by 1, and that's certainly better than the previous line. What we want is a way to not have to manually be making these guesses and intercepts, although there's nothing wrong with doing it by trial and error. The only challenge is to be sure that you start out somewhat close, although there is a sneaky way to start out close. If we set the slope as 0 and intercept, I think of 100, it should put a horizontal line in right there. We want something better than that. Let's just first let's look at our tuple. And so the values we got was 580, 97, 630, 103, compared to our earlier one, which was 580, 96, and 630, 106. So we're pretty close to the same one. Let's now apply the linear regression approach, where we're actually going to take our slope and intercept from these expressions right here. Kind of like back when we used the mean and standard deviation to fit our observations to a normal distribution. So here's the script to evaluate the normal equation. So we need sum of x, sum of y, sum of the cross product xy, sum of x squared, sum of y squared. So here we've just created a place to store those, all set to 0. These are going to be accumulators. And then we'll just run through sample weight, the n number of things that there are. The length of sample weight, which is supposed to be the same length as sample length. So the sum x is we take what was there, we add the value of sample weight, the ith item, to it, and then keep working through. Sum x squared, we take what's there, we add sample weight squared. Sum y, we take what's there, we add the sample length. Sum y squared, we take sum y squared, what's there, add to it sample length squared, and then the cross term, sum of xy, we take what was already there and we add to it sample weight times sample length. So those are the 1, 2, 3, 4, 5 terms that are right there. And then we evaluate B1 as the, according to the formula that was up there. So B1 is sum x, sum y minus n, sum xy divided by sum x quantity squared minus n, sum of x squared. And then beta 0, again, following the formula. And then we're getting a little fancy with our output. And we will have it report our linear model. It says our linear model is 0.129 times x plus 22.813. So let's go ahead and take these values and we'll put it back up here into our trial and error, and we'll see how that does. And what we'll find out is it does great. And there we are passing the normal equations through. And here it's actually done for us. So there we go. So that's essentially what one part of linear regression involves. Finding the slope and intercept to produce the red dashed line. And that red dashed line has the property that the deviations, the distance from the blue marker up to the red line, if you take all those deviations and square them and then add them up, that will have the smallest value of deviations squared added up of any other line that you could draw through there. It's called the least squares condition. So where do these normal equations come from? Well, let's consider a linear model. Y equals beta 0 plus beta 1 x. And now we'll put this little epsilon here. And so that's the error in the estimate. So epsilon, you can think of it as it represents the distance between the blue marker and whatever the red line is. So if we square each of those errors and then add them up for our training set, so this set of blue markers can be called a training set, we have the property that the sum of the epsilon squares is equal to the sum of y minus, oh, I have a sign error there, let me fix that. That's why they didn't quite. Come on, you silly machine. Okay. Y minus beta 0. Okay, that's going to make the calculus work so much better. There we go. Of y minus beta 0 minus beta 1 x quantity squared. Our goal is to minimize this error by choice of beta 0 and beta 1. I'll check something before I lie even further. Ah, that's okay. I have that sign error everywhere, so I'm going to attempt to fix it while I read through it. So we want to make the sum of epsilon squares as small as possible. And we're going to do that by choosing values of beta 0 and beta 1. And so we're trying to minimize a function. And the necessary and sufficient conditions for a minimum is that the first partial derivatives of the error of this stuff here as a function must vanish. And we can leverage that requirement and come up with a formula to find the unknown value of beta 1 and beta 0 that make that true. So let me first make the corrections to my deal. Okay, I think it's correct from there on. Yeah, that's better. So we want to take the partial derivative of the sum of epsilon squared with respect to beta 0, which is the partial with respect to beta 0 of the sum of y minus beta 0 minus beta 1x quantity squared. So the only term in here that involves beta 0 is that beta 0 right there. So that becomes minus 2 times yi minus beta 0 plus beta 1x, which is minus 2 times the sum of y's minus n beta 0 minus beta 1 times the sum of x's, and that's all set equal to 0. So here we have one equation with two unknowns. The two unknowns are beta 0 and beta 1. Everything else in this equation is known except for the number 2, which we get from Count Dracula. He loves to count. 1, 2. We do the same for beta 1, and the terms involving beta 1 are right here. So there's a beta 1 squared, and the derivative of that is 2 beta 1 d beta 1 d beta 1, so it becomes 2 beta 1. And so we end up with a minus 2 times the quantity y minus beta 0 plus beta 1 x times x, which is equal to minus 2 times the quantity sum xy minus n beta 0 sum of x's minus beta 1 sum of x squared equals 0. Here's our second equation. Again, the unknowns are beta 0 and beta 1. So we now have two equations in two unknowns. The two unknowns are beta 0 and beta 1, and the two equations are the two first partial derivatives of the error function set to 0. And they're linear. They're linear in beta 0 and beta 1. So two equations, two unknown, linear, almost trivial to solve, except for this goofy notation. If we go through the algebra to find the two solutions, we'll discover that beta 1 is sum x sum y minus n sum of xy divided by sum x quantity squared minus n sum of x squared, and beta 0 is equal to 1 over n sum of the y's minus beta 1 over n sum of the x's, and we replace the 1 over n sum x's, 1 over n sum y's with x bar and y bar. So that's a really brief introduction to the theory. Let's consider a slightly more flexible way to do this, and I think you'll see the utility of the more flexible way shortly. Let's do it in a computational linear algebra structure. So we're going to replace all these summations and this stuff with matrices and vectors. So we'll again start with our linear model. Y is equal to beta 0 plus beta 1x plus epsilon. We'll replace it with vectors. The first vector is we have the observation vector, cap y, which is comprised of y1, y2, dot, 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 yn. We have our beta vector, a parameter vector, which in this case only has two terms, beta 0 and beta 1. And we have an X matrix. So what the X matrix contains is the first column contains ones. Those are what are going to be acting on the beta 0 term. And the second column contains the x1, x2, ... x sub n things. And lastly, we have our vector of epsilons, epsilon1, epsilon2, all the way to epsilon1, all the way to epsilon n. And so now we can express our system in matrix vector form in the following linear system equation. Y, the vector, is equal to x, the matrix, times beta, the vector, plus epsilon, the vector. And if we perform the same calculus as before, what we end up with, I'm going straight to the results, is a result where we will pre-multiply the linear system by the transpose of x, and what we will have is a system that's linear in beta, which we can solve by Gaussian reduction, LU decomposition, or some other linear equation method. And what we're minimizing is epsilon transpose epsilon in vector form. And the resulting system that makes that true, that makes epsilon transpose epsilon a minimum, is x transpose y equals x transpose x times beta. The formal solution to that is to take x transpose x and invert it, and then multiply that by x transpose y, but that's the stupid way to do it. What we're going to instead do is solve this linear system using a Gaussian elimination method. So here I've gone to the internet and found an appropriate linear solver. The key was to find it with pivoting. And so this URL goes to a interesting question and answer post from which you can pull out pieces of this script here and assemble it, and you have a working script. So what this does is it does Gaussian elimination with pivoting on an arbitrary system AX equals B, and it returns the value X. Then we need a script to do some matrix multiplication. So this one is a matrix multiplication script, and it multiplies two matrices. We need that because we're going to have to do matrix multiplication here and there. Then we also have a script to do vector multiplication. So I lied. There's our vector multiplications right there. So this is just computational linear algebra. You would have had it in calculus, or you're going to have it in calculus. So the multiplication of matrices is slightly tricky. Naturally, NumPy probably does it for us. And now we'll go ahead and actually build our model. Our X matrix has two columns, and it has the same number of rows as sample weight. And so here we're going to create a list for the X matrix. We're just going to fill everything with ones for the time being. And then we're going to create a list for the X transpose matrix. So a matrix and its transpose is the rows and columns become interchanged. So here it's going to index on row numbers and then on column numbers. And again, we'll just fill it with ones. So the X matrix is going to have 6 rows and 2 columns in this particular example. And the transpose matrix is going to have 2 rows and 6, I think there's 6. Let me go up here and look. 1, 2, 3, 4, yeah, 2 rows and 6 columns. And we have the Y vector, which we will populate shortly. So that's just pre-fill it with zeros. Now this is an interesting construction that I've not shown you before. I think that's actually, I think it's called a constructor way of filling lists. And what I'm doing is putting zeros and ones into lists. And what that lets me do is that lets me do ordinary assignment rather than doing the append method. And there's, in this case, there's an advantage to that, because now I'm just going to march down through the number of rows in our problem, which in this case happens to be 6. There's 6 pairs of XYs. And so the X matrix, the column 1, so column 0 is all ones, but column 1, we're going to put the sample weights in. The X transpose matrix, row 1, there's a row 0, which is going to be just filled with 1s. We're going to put the sample weights in. And finally, our y vector, we're going to put our sample lengths in. So weight is predicting length in this case. And then we're going to produce an output matrix called X transpose X and X transpose Y. And these initially are just placeholders, so there's a place to put data. The X transpose X, because it's a formal matrix, has to be constructor built. X transpose Y can just be a null array. And now we're going to perform matrix multiplication. X transpose X times X matrix produces the XTX value, and then the XTY value is matrix vector multiplication, X transpose Y vector. So just a little linear algebra right there. And now we're going to solve the linear system. So we're going to create a placeholder to put the results. It's going to be called beta. And our linear solver, we supply it with X transpose X and X transpose Y. It's going to produce beta. And our slope will be contained in beta 1. Our intercept, beta 0. We'll go ahead and use the X low and X high as before, and we'll let it go ahead and generate the plot. So the linear equation solving is right there. So that's setting up the problem as X and Y matrices and vectors. Our linear equation solver is this wonderful piece of code that will not show on a single page. And then we have some utility functions that are obviously specific to my script. So when you do this yourself, yours will look different. I'm pretty sure all this functionality is replicated to some extent in either NumPy or Skippy or Pandas. And we'll go take a look at that. It looks like we're good on time. We can try to adapt this for that one. So let's go ahead and run this. So let me load in the solver. And there is our picture. So look at that picture, memorize it. Look at that picture. Are they the same or are they different? Well, I guess technically they're different, but they sure look an awful lot the same. So there is our system solved using linear algebra. Well, that begs the next question. You know, what's the point of that? You've just gone from something that was easy to something that has like pages of gibberish. And yes, that's true. The value of the linear algebra approach comes when we have more than one explanatory variable. So for example, let's say we want to deal with curvature. So let's look at this picture. So here we have two lists, YYY and XXX. So XXX predicts YYY. We'll just pick a slope of a half and an intercept of 1, and we're going to plot from -3 to 3. And this is all the same script, just a different list. And let's see what we get when we do that. Okay, so there's our red dashed line. And the question I have is that a very good predictor line or not? Anybody? Okay, so you're not willing to take a stand on that, that's fine. That's a pretty good straight line, but for one thing, we know it's not necessarily the best straight line because we haven't gone to any trouble to try to use a regression tool. So let's go ahead and do that. Make sure this is the right one. Yep, that's the. So there's the best straight line through that data. But let's play a little bit. Let's suppose we add a third column to our X matrix. And that third column is X squared. So our linear system now is Y equals beta 0 plus beta 1X plus beta 2X squared. So we'll try to fit a quadratic through those dots. So all we have to do to modify our script is add the third column to the X matrix and the third row to the transpose matrix. I've changed absolutely nothing else. Two things. Let's run it now. Okay, so now we've run it. No plot, because that plot won't work for us. And so here we're going to go back to our, I think lesson 11 or 10 or 11. We're going to go ahead and make a model based on the data we just created, the model we just created. So beta 0, beta 1, and beta 2 are obtained from this linear fit. And then we're going to plot the 2 on the same axis. And let's go ahead and see if I can get the marker to do a dashed line, because I just think that's cool. Although solid line's fine. K dash dash. And if it doesn't work, we'll just take it out. It does not work. So fine, leave it be. Well, now I'll plot the 2 lines. This is the same script we were using to plot red lines on blue markers way back in lesson 11. And there's our new plot. And so the question is, does the red line do a better explanation of these data than the original straight line?
A bit better.
Yeah, it's a much better fit. And so the only change we made was just adding a column, a new explanatory variable. And that's how multiple explanatory variables are done in practice. They don't have to be X squares. It could be a whole different data source. And if we wanted to be fancy, if we went from -2 to 2, since I generated these data from a quadratic, I got to go to +1, don't I? There we go. I've been wondering why it was looking funny. So there's our fit. Okay, so now we want to do everything using NumPy. And I've got 20 minutes. So how would I go about doing that? Well, I would go here to, let's see, see what we get with NumPy linear regression. So Skippy stats line regress is one option. Linear regression in Python. Linear regression with only Python and NumPy. Oh, that one looks intriguing. Let's see, it's a GitHub, so that might be hard to get running in 20 minutes. Linear regression with NumPy. So which one would you all choose? Anybody? NumPy do thing. Let's try this one, because this is what I just did in I think I found the source of the other one. Predict using coefficients. I like that one. Everybody like that one? So how do we proceed? First, we have to get the data, and then we can build it. And I want to see what the NumPy looks like. This is one of the, he's doing it by matrix inversion. That's stupid. Oh, whoever wrote this is not the brightest. That's mean of me to say. I have hits there, mine's not. But we will save that for another time. What I think would be better is to go into the laboratory, and I'll let you play with some of these. So I am going to stop sharing. Check the, yeah, okay, so whoever said not the .org, that is good advice, because, oh, what's wrong with inversion? Okay, so Rame asks a very good question. What's wrong with inversion? Let's say we have a system that's a 5x5 matrix. To do inversion, you have to do 5 times as many multiplications and divisions as you'd have to do to solve a single linear equation with the same matrix. So if you can avoid inversion, you want to avoid inversion. Because inversion, you can think of it as it's solving 5 linear systems to get the inverse, using 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, and so forth as right-hand sides. And if you don't need the inverse, there's no point in doing it. So it doesn't matter with small things. Little 20 by 20s are smaller. It doesn't make much of a difference. But when you start doing these with 25,000 rows, inversion is, well, it's essentially, well, it used to be impossible, probably not anymore, but it's not the best use of computer time when it could be serving up meaningless plastic trinkets on Amazon, or cat videos, dog videos for those of you who like those. I'm going to put Farang and let him do the lab if I can find him. That's me. There he is. Are you ready?
Yes, sir.
Okay, I lost you again. Let me find you again. There you are.
Thank you. Shall we go with a 5-minute break?
Yeah, I'll go ahead and do maintenance to address these issues that were in the chat box.
Okay, so it's 9:03. We're gonna start at 9:10.
Yep.
But if you have any questions for me, I'll be here.
Okay, someone had a message. Nap time. 10-minute nap. That's good. Project directory goes to lab 19. Okay, so that is over here.
Oh, so Dr. Cleveland, a few things came up in the chat box. They are saying that the link you have there for the project takes them to lab 19.
Yeah, I'm
directory.
going to go ahead and try to repair that. I must have made a mistake when I did the link.
Yeah, and then they're asking for the winner of the popular vote for the costume.
I
session.
haven't tabulated that yet. We'll get all that Thursday. Even probably get grades on Thursday.
Okay, cool. So everything will be for Thursday, guys.
Yeah, it sure does go to the wrong directory, doesn't it? Damn machine. Okay. 6 dash. Okay, that goes to.
Yes, Rame, you indeed need then the class notebook and 2 CSV files that you will find there, the advertising and the cars.
That's a cool brain gift, man.
That is weird, Rami. It shouldn't give you an error. So you can download the other CSV file with no issues? Interesting.
Okay, it looks
Yeah,
like
it works on my computer.
yeah, let's make sure he's taking the right advertising. I think there's one in pseudo lesson. Yeah, they happen to have the same name. Let me hide that one. I'll rename it. Okay, lab 19. Advertising is perfectly good. And let me check it from here. Lesson 19, laboratory 19. It downloads for me too.
Rami, did you manage to download it? Brandon, to be honest, I don't know. I do not use GoCalc anymore.
Oh, if you're trying to download the CoCalc, that's not going to. No, I guess that should work. You can. You have to download then upload.
Yeah, Rami is saying that it's probably a browser thing. It could be. If you manage to get it from the chat box, that's all right. All you need to do is to have it in your working directory.
Yeah, Rami, are you on the Texas Tech network right now? Because if the answer is yes, then it is a browser thing. Because
He says he's at home using his own network.
it shouldn't. You shouldn't encounter filters. If you're on Texas Tech, we have the safest network on the planet. Nobody can use it. Not even the Russians or the North Koreans.
I thought you were going to say not even ourselves.
That's where I was headed to. So on the projects, I know that people are listening, and that's fine. I don't have them all finalized yet, but I've uploaded most of the pieces I have, and probably later today or tomorrow, formal problem statements will be available in those topics. I would recommend people go look at them now and get an idea for which one they think they want to work on. The one on image classification is not going to happen this semester, so don't bother on that. And I'm not sure that the digital rights management one is going to happen. So the ones that I think will get finalized are the one that's I've called instrument calibration.
Mm-hmm.
And if people want to choose that, you need to pay very attention to this lab and the upcoming ones. The concrete strength one, which most of people in this class have already successfully downloaded the file once. So the hard part is taken care of. Now you have to do is figure out what to do with it. And the music classification one. So those ones I think will be available for sure. And then the other two, I don't know if we'll get far enough this week to really be able to deploy them.
I think 3 is flexible enough.
Yeah, I do too. And they only have to work on one. Well, they have to complete one. I don't care which one. They got to complete one. And I haven't put the team thing together yet. I'll hope to do that. I'll do that by Thursday. That's enough time for me to learn how to do
once we take care of all those, we can make an announcement and let everyone know.
All right. But if anyone wants to, It's going to be one project per group, correct? But take a look at what's there, because that'll give you a feel for what your instructors are thinking are appropriate projects. And bear in mind, some are further along than others. And Rame, you get to work with virtual people.
I've never seen anyone so excited to work with people, Rame.
Except a surgeon. I get to work with people? Okay, I will, I've got the link working, I think. Yeah, actually it's working correctly. Let me test it. Yep. So that's working, and I will let you go on with the lab. And I want you all to pay attention to the lab. This is a good lab he put together for you. So you're going to learn a lot.
So let me find my tab. Okay. So can you explain the project again after the lab? Lee, I'm not sure that it will be possible time-wise, but once everything is up there, we'll make an announcement and share the details and the framework with you. But if we have time, Dr. Cleveland will be here and he will go over things. So lab 19, this is already 9:12, so I'm going to assume that you are all here and you have downloaded the 2 CSV files. And what link doesn't work, Max? It is kind of weird because some of us are downloading the same thing, but if it doesn't work for you, just go in the chat box and you will find the CSV file. Here, I think Braden put it up. Yes, Braden uploaded it in the chat box. You can download it from there. So one notebook you are going to use. Actually, let me go ahead and work on the same one so that it doesn't confuse you. Lab 19 class. So this should be the notebook that you have. In case there's a spelling mistake here and instead of 19 says 18, you can go ahead and fix that. But I think the version that is on the server is already corrected. If you have no questions on this, we can actually proceed with the lab. Are we all good? Okay. Yeah, that was a special message for Rame. He was very, very interested in my tabs before, so I just arranged a little something for him. Okay, so you have already become familiar with linear regression and the general context during the lecture. I am going to start from something a little different in looks, but not very different in nature. Let's say that we have these sequences here, and I'm asking you to guess the next step of each sequence. And you, with the assistance of your brain, of course, are going to answer my question. So we have A, B, C, D, E. And what do you think the next step will be?
F.
Do we have any other answers other than F? No. Okay. We have 5, 10. Yeah, Rama said 6. Why did you say 6, Rama? Should I even wait for your answer? Okay. So 5, 10, 15, 20, 25,
and 30.
30. That's the only answer that I'm getting, both in the chat box and from the mics. Okay. 2, 4, 8, 16, 32,
64.
64. Interesting. I have never seen you have such mutual understanding on something. That is very interesting. 0, 1, 1, 2, 3,
5.
5. And someone said Fibonacci. 1, 11, 21, 1211, 111,221. What's next? Three, 1, 2, 2, 1, 1, 1, 1, 1, 1, 2, 2, 1. Is this that fancy thing like pi E1 or something? Well, at least we can agree that in the last one, we are not as certain as we used to be with the other sequences. And Rame, you're getting very close. Yes, it's the look and say sequence. We're going to talk about that in a moment. I have a question for you. How did you guess the next item in each sequence? Is it that you are all so familiar with these sequences that you know all the items in them? Is it that there is only one possible next step? Is it that I have given you the first 5 items? Patterns. So, Brandon, Cody, Braden, those of you who said patterns, can you elaborate? What do you mean by patterns?
I basically just noticed the fact that like they increase or they change by a certain rate.
Okay, that is a very good answer. Do we have anything else?
They all follow certain series rules. You could express them in an equation. So like A, B, C, D, E would just be +1, or the next one would be +5, or ×2, or then plus the previous iteration.
Okay, so based on your answers, would it be fair if I say that you identified the relationship between these items, and using that relationship, you guessed or predicted the next step?
Yeah.
Do we all agree on that? Yes, no,
Yeah.
maybe?
Yes.
Okay. So that's something that I wanted to reach at first. But about these sequences, the last one, as Rami already mentioned, is the look and say sequence. So basically, you look at the first item, which is a 1, and you say, okay, I'm seeing 1, 1. And then on the next step, you say, okay, I'm seeing 2 1s. And then you look and say, I'm seeing 1, 2, and 1, 1, and then so on. That is the relationship between the different items. And the one before that someone already mentioned, it's the Fibonacci sequence, also known as the golden ratio, also known as the God's fingerprint. To be honest, at this point of my life, I'm still amazed by photos like this and the repetitive pattern of this sequence in the nature, but I'm not sure if it's something given to us by the media or if it's really something that's there. Either way, it is kind of amazing. So now we talked about sequences of 1 items, like the ones that we've already discussed. What if instead of a single sequence, we have, let's say, like 2 sequences, and we want to predict the next item in one of them, knowing that the other sequence has some kind of relationship. Is this situation kind of familiar for you? Yeah, from where? Yes, pretty much. But in this class, we have done that actually more than once. So the blue points, the red lines, getting the fit. If it is bringing back something, I'm happy. If it's not bringing back anything, I really don't know what to say. I just suggest that you go back and review some of the lab notebooks. But in your exam 2, your problem 1 was something like this. We gave you a table with 2 sets of recordings, elapsed time and speed, basically 2 sequences. And then we ask you to plot it, to plot them with blue markers, and then plot a red line using an equation like this, f of x equals to mx plus b. And then by trial and error, find the values of m and b that provides a good visual fit. And then use the data model to estimate the speed at t equals 15 seconds. Is this something you remember?
Yes.
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 Okay, cool. What you did in that problem in the exam was basically a linear regression problem. Now, because we had not taught you this, you used kind of a primitive approach on it, and you went with trial and error, and you kind of were uncertain about your final answer. You didn't know if you have truly reached at the best fit, but as long as it was giving you a visually acceptable line, you were happy with it. Today, we are going to talk about the main tool to tackle a problem like this. Linear regression is a basic predictive analytics technique that uses historical data to predict an output variable. What do we mean by historical data?
Those are our sample points.
Thank you very much. Yes. So in an example like this, these will be my historical data. Do not let the word historical give you the idea that we are looking at years and years and decades of data. No. Basically, they are samples. They are observations. They are things that we have already monitored, recorded, noted, blah, blah, blah. So the predictor variable, or the input of the linear regression model, is the variable or the variables that help predict the value of the output variable. It is commonly referred to as x. In this example, which one was our x? Time. What is TM, guys? So it's time. And why do you think that it's time? Why not speed? Because time is independent variable. That is a fancy answer, but why do you think that? More consistent. When you say time is independent, what do you exactly mean?
Like time moves by itself. You don't have to do anything to make time change. So, I mean, the speed would just be dependent upon like what point in time you're observing it at.
I think I know what you're saying, but in a case like this, you actually have no control over time or speed. You are just simply making notes of an observation. So both of them are out of your control. And I'm liking some of the things that I'm seeing in the chat box. It is not really in the scope of this class to go in depth with dependence and independence, but generally, when you are given an item and you are asked to predict another one, the one that you have is your input and the one that you want to get is your output. So using this data model, estimate the speed at time t equals 15 seconds. So time is your predictor, is your input, and the output that you're looking for, or your y, is going to be speed. But thank you very much for your answers. So the output variable is the variable that we want to predict, in this case, speed, and it is commonly referred to as y. So in a general format of a linear regression, x is the predictor, is the input, and y is the output. Are we good on that?
Yes.
Cool. To estimate y using linear regression, we assume the equation y of each, it is basically the estimated y value, equals to beta multiplied by x plus alpha. Does this format remind you of something?
Y equals mx plus b.
Exactly. Exactly. So simply instead of alpha and beta, we are using b and m. But the format is the format of a linear equation. In an equation like this, what do we call beta?
Slope.
Thank you. And what do we call alpha?
Intercept.
Thank you. So keep these in mind. These are building blocks that we are going to use a lot in this talk. Yes, where y is the estimated or predicted value of y based on our linear equation. So our goal is to find the statistically significant values of the parameters alpha and beta, or m and b, that minimize the difference between y and ye, the actual y's and the estimated y's. If we are able to determine the optimum values of these two parameters, then we will have the line of best fit that we can use to predict the values of y given the values of x. This is a very important statement. Read that again and tell me if you have any questions about it. Are we all good? It says y and ye, correct. So in this example, a very good, Brayden, yes, y is our speed, is our actual values that we have observed in our historical data. ye is the estimated value, is the value that you get from your line or your linear model. Rami, that is absolutely correct. Regression is finding the best fit line. But let's just assume that at this moment of time, we are talking about linear regression only, and we are limiting the entire regression family into only linear regression. Yes, Dooley, that is actually a very good conclusion of this. The entire goal of linear regression is find the best values for your intercept and slope, which means that you will arrive at the equation of the best fit. Do we have any other questions about this statement? Yes or no?
Nope.
No. Okay. Now that you know the goal, we need to know the method. How do we estimate alpha and beta? How do we get those values of the best fit? For that, we can use a method that is called ordinary least squares, or OLS. The general idea about OLS is something that I believe you will have no issue of thinking about. Let's say that these red points were our historical data, or our observations, or our samples. And I have this blue line as my curve fit. When would you say that this is the ideal fit?
When the average distance between the data points and the curve fit is the least.
Very good, but generally I would call that an ideal fit when there were no distance. So where I could draw a line that would go through all of those points with no distance. That would be ideal. But for many reasons, that is not possible. One of them can be simply that the behavior we are observing is not linear. So when we draw a line, there will be a distance between the observed points and that line. For each point, there will be a distance. One way of finding the best fit is to find a line that has the minimum average distance. Does that make sense? I want to draw a line that falls closest in average to all my points. Is it possible to have multiple? Multiple what, Braden? You can shift the line. That is actually the process that will happen. But there will be one specific situation, one specific location of that line that will give you the best fit. And that will be your line of best fit. Now, let us proceed. The objective of the least squares method is to find values of alpha and beta and minimize the sum of the squared difference between y and ye. Let me ask you another question. What is this green line? Do I have a name for that?
Ellipses.
That is very fancy. Do I have any other words for that?
Is it like the change in y?
Getting kind of close. Distance is also kind of close. Variation is not something that I would use for this case. Okay, let me rephrase the question. Let's say the value that we observed, this red dot, is 6. When I predict the value for that point, I get 5. What is that 6 minus 5 called?
The error?
The error, yes. So each of these lines, each of these green lines, are the errors in estimation of each point. But when I want to look at the entire thing, the entire range of samples, I'm looking at the entire error of my model. Margin of error is defined based on a distribution, Braden. In this case, we are just talking about error. So the difference between y and ye is basically the distance between the linear fit and the observed points, shown in green in this plot. We'll not go through the derivation here, but using calculus, we can show that the values of the unknown parameters are as follows. So if we take the derivatives, we set them equal to 0, we will be able to calculate beta as this and calculate alpha as this. So basically, when we know the value of beta, it is very easy to calculate the value of alpha. Now, I have a question for you. Look at the denominator in beta and tell me whether this equation here looks familiar to you.
It looks like variance.
Exactly. Thank you. It looks like variance, and it is variance.
Mhm.
So where in this equation, wherever we have x bar, that is the mean of x values. We get that from our samples. And y bar is the mean of y values. Again, we can get that from our samples. Beta is simply the covariance of x and y divided by the variance of x. So what you see right down here is the variance of x. What you see on top is the covariance of x and y. For those of you who have not been in a statistics class before, this might be a new term because we have not talked about it before. And that's something that is going to happen right now. So covariance, it's all right, Rami, don't worry about it. Covariance in probability theory and in statistics is a measure of the joint variability of two random variables. This rather fancy statement basically means that looking at the covariance of two variables, we can say whether they behave similarly, or they behave completely differently, or they behave independently. So let me ask you a question. Do you think there is a relationship between temperature and ice cream cells?
Probably.
What kind of relationship?
Higher temperatures equals higher sales.
Thank you very much. In a case like this, we will have a high covariance. We can say that by increasing temperature with greater values of temperature, we are going to have greater number of cells in ice cream. So high, high. How about temperature and selling boots?
No relationship.
Is it no relationship?
Or,
Winter boots.
Not of, oh, never mind. Then it would be, yeah, the colder it is, or the lower the temperature, the higher the sales, so inverse relationship.
Exactly, that will be an inverse relationship. So there is a relationship, but it's not high-high, it is actually high-low, right? Now, is there a relationship between temperature and I don't know, the income of an instructor?
I guess technically, because you don't work over the summer and it's hot in the summer.
Well, we do work in the summer.
Yeah,
We
but for
have
free,
9-month
right.
contracts, but we do work in the summer.
Oh, well, for like elementary school teachers, I guess.
Oh, yeah, but
was good.
think about me as a poor PhD student who works 12 months a year on the same salary. So it doesn't really matter if it's July or November, I'm getting the same amount of money. And just for the sake of my example, in this case, we are going to say there is no relationship. So it's not high-high, it's not high-low, it's basically two completely different things. we can use covariance to pass a judgment like that on two variables. The covariance is positive whenever it's high. The covariance is negative whenever it's low. And then the sign of the covariance shows the tendency in the linear relationship between the variables. The magnitude of the covariance is not easy to interpret because it is not normalized and hence depends on the magnitude of the variables. So you cannot say a covariance of, let's say, 5 is always high, because it really depends on what variables you're using and their range and variability. The normalized version of covariance is called the correlation coefficient, which we will discuss in a bit. So the formula of covariance is given to you, and it's basically right here as well. This is basically a visual explanation of what we just discussed. So high will be positive correlation. 0 means basically no relationship. Negative correlation is the high-low situation. Braden, that is a very wise observation. In many cases, yes. Yes. AJ, at this point of my life, when people say that I should have got into business, I would just tell them, bummer, it's too late. But yeah, maybe it was an easier path for you. I don't know. They're not as cool, but they make more money. So that's your call. The correlation coefficient is basically the normalized version of covariance. And the cool thing about it is that it always falls within the same range. So it always falls between -1 and 1. And with the same logic that we discussed, whenever it's higher and it's closer to 1, it means a stronger positive relationship. And whenever it's more negative and smaller and closer to -1, it means a stronger negative relationship. And whenever it falls around 0, it basically means no correlation or no relationship. Are we clear on this? These are very important fundamental things that you will need in your toolbox for the future.
Yes.
Okay, cool. Now, let us actually do some coding. We are going to use your problem 1 from exam 2 to kind of give you a déjà vu of that nightmare again and prove a point about linear regression. So we have this table, and we are going to go through different steps and talk about them individually. So first, let's create a data frame. Time, speed. I'm naming my data frame data with 2 columns, and it's basically the same table, but now it's a pandas data frame. I'm going to explore my data. I have basically 11 observations. My mean speed was 43. The standard deviations are here. The 5-number summary is here. And that's basically what we mean when we ask you to describe a data set. We are going to calculate the variance of time and speed. We are using the statistics package. We are using the function named variance from that package and run it on my time object and my speed object. So the variance of recorded times is 11, and the variance of recorded time, this is another typo by me, sorry. Speed is 1697. Now we want to answer the question, is there a relationship Could we also, exactly, yes, yes. Standard deviation is the square root of variance, so you could take that to power of 2 and get the same thing. Yes, you're right. Is there a relationship based on covariance and correlation between time and speed? From the pandas library, if you simply run this function, .cov stands for covariance, on your data set, you will get a table like this. Time, speed, time, speed. In time, you're getting 11. What does that mean?
The max value of time at time is 11.
Even though that we are looking at covariance, when both of your variables are the same, in this case time, that will give you the variance, right? So covariance means looking at two variables. Variance is only one. So actually the 11 and 1697 are the ones that you will find on this parts. And then the covariance between time and speed is 131.75. What can you infer from this number? Positive. What does that mean? Slope-wise positive. Yes. What does that mean?
As time goes up, speed goes up.
Yes. Or as Braden said, high. Yes. So for higher values of time, you expect to see higher values in speed. That is one way to infer. Now, we can use this function, CORR, and by the method Pearson. There are different methods to calculate correlation coefficient. Pearson is the most common. If you're interested in reading more about them, you're more than welcome to. There are some limitations to some of them, but generally Pearson is a good go-to. So when we get that, we get another table. And for time and time, I have 1. What does that mean?
It's the same variable.
It's the same variable, of course. So when this one goes up, the other one goes up, and both of them are the same thing. So generally, if you're doing some research or working on a problem or something, when you get a correlation of 1, it is always better to double check your code and make sure that you're doing the right thing, because it is kind of weird for two variables to have a correlation of 1. That is just too good to be true in many cases. For speed and time, we are getting 0.96. What is the meaning of that?
They're very correlated. Positive.
They are very correlated. In what direction? Positive. So looking at this number, you can infer information about the direction of the relationship and the strength of the relationship. These are two different concepts that are beautifully described by one metric in this case. So speed and time in this case are positively related, and they are strongly related because the value is very close to 1. Braden, I'm not sure what you mean. If it is very close together, then just not related. I can't read that sentence. If the value you get is close to 0, that means that they basically have no relationship. There's no correlation. Did I answer your question? Okay, cool. So the direction of the relationship is something that you can infer from covariance, but the coefficient of correlation is always a better tool, because not only it gives you the direction, but also it gives you the strength of the relationship. Now, let us go on and do linear regression with primitive Python. How am I going to do that? Unmute or share your opinions in the chat box. How do you think we can do linear regression? Yeah, these are all good ideas, but you already know what you need to do. So just scroll up in the same notebook, look at the notes, and tell me what I need to do. Use the formula. Which formula? Which one? OLS. Okay. What am I doing with my OLS functions or equations? Beta and alpha. What are those?
I guess define beta as a function, or use all your values to find beta, and then use it in the alpha function to find your linear regression.
Okay, and thanks all of you who are in the chat box as well. That is correct. So I'm going to use these two formulas to calculate my beta and alpha. And once I do that, I can find the equation of the best fit line, and then I can just plot it and then make predictions and whatever I want to do. So going back to here. To estimate y using the OLS method, we need to calculate x mean and y mean, the covariance of x and y, and the variance of x, before we can determine the values for alpha and beta. So, as we've already discussed, in this case, x is time and y is speed. So, I use the mean function from the NumPy package to calculate the mean and the mean for x and y. Then I basically calculate the covariance of x and y by going through the formula. I'm saying my data records minus their mean multiplied by my speed records minus their mean, and that will be the covariance. My x variance will be my time samples minus their mean to the power of 2. And I'm doing this in a very primitive way because we first want to do it in primitive Python so that you know what is happening behind those relationships. Once I have all my requirements, I can actually go on and calculate my beta as my covariance divided by variance, and my alpha will be my y mean minus beta multiplied by x mean. These are the two equations we have on top. And then I'm going to print them, and based on this, my value of alpha is minus 16.78, and my beta value is 11.98. Do any of you remember the best M and B values you found in the exam? That would be surprising.
I can pull it up, but I don't remember off the top of my head.
Now, I don't want you to spend time on it, but you probably landed somewhere around these, but not exactly on them. I think I had minus 17 for y. Yeah, so that would be very close. Okay. We now have an estimate for alpha and beta. Our model can be written as estimate of y equals to 11.977 multiplied by x minus 16.786. And when we have that equation, we have that line equation, we can go on and make predictions. So I'm defining a NumPy array with my time values. I'm naming that x. And I'm basically writing this equation. So my ypred is going to be equal to my alpha plus my beta multiplied by my x. And if I print that, these values are my predictions for speed based on my linear equation. So these are estimates. These are not observations. Does that make sense?
Yes.
Now, if I want to get my error, what should I do? How can I define my error based on the values that I have? Subtract those from the real points. Thank you. What do you mean by real points? What should I subtract here?
From the historical points or the given points.
When you say points, points has two coordinates.
The speed.
Thank you very much. Yes. So if I subtract my original values for speed, which were my actual y values, from these, which are my estimated values, I will have my error. That is very important for you to know. Okay. Now we are going to plot our prediction ypred against the actual values of y to get a better visual understanding of our model. So my first plot will be my x against my ypred, the red color, the red line. And I'm also plotting my time against the speed with blue points. And the rest is just fixing the looks of my plot. So based on this, what can you tell me about the errors?
It'll be kind of high since the data points follow a curve rather than a line.
Okay. Do you think that this line has low errors or high errors, or what can you tell me about errors at this point?
For a linear line, the error is pretty low.
Mm-hmm. What else? So high errors, the error values vary. What do you mean by that, Dule? They are not all the same. Yes. So for example, for a case like this, you basically have no error. In a case like this, you have slightly more errors. In a case like this, you have even more. So for different points, you will get different errors. Yes. If you had more points, it would have more error. Not necessarily. Maybe I had more points around this area, but maybe if I had more points, I would have observations like here. So you never know. You can only pass judgments based on the samples that you have. So this is a visual assessment. This is very similar to what we used to do even before this whole thing. And now, if we want to predict, what should we do? First, what do we mean by predict? Look at line. No, predict doesn't mean look at line.
You can extrapolate the line.
You're getting very close. Plug in values.
Use the line to estimate future other values.
Yes. I want to put whatever you said together and say, if you are given a data set that in this case goes from time 0 to time 10, but you are interested to know what will happen here at time equals 15 or times equal 20 or times equal 50. You do not have that data. You do not have that point in your samples, but you want to know about it. That will be prediction. That will be guessing. That will be, depending on the nature of the problem, forecasting. don't get into the detail of difference between forecasting and prediction. But just keep in mind that in case of extrapolation beyond your sample points, if you want to use your equation to get an estimate, that will be prediction. Now, I have my line equation. If I go in and instead of my x value, which is my time, put x equals 20, I will get this value, 222 as my speed. So this is telling me that if my plot was kind of extended up until probably around here, if I went up, that would be around 222 meters per second. Does that make sense? Yeah?
Yes.
Cool. Now, whatever we did was in primitive Python. There are external packages that we can use that are kind of easier. So we're going to have a look at linear regression with a stats model. First, we use a stats model's OLS function to initialize our simple linear regression model. This takes the formula in this format, y, x. Do you know what this sign is called? No?
Approximately.
Come again?
Isn't that congruence or something?
I mean, do you know the name of that sign?
Tilde?
Tilde, yes. So it's interesting because I never knew that until I came here. And it was in my first semester that one of my professors said tilde. And I was like, huh? I didn't know I had that on my keyboard. So yes, that little sign is a tilde. But in this format, you are basically saying that I want my y based on my x. Yes, Rame. Yes, that is one of the most common applications of that in gaming. So where x is the predictor variable and y is the output variable. So basically, you will have what you want to predict, tilde, what you want to use as your predictor. Then we fit the model by calling the OLS subject fit method. So what is happening is here. I'm calling the SMF function from my stats model formula API. And the format is this, smf.ols, speed, my output, tilde, my input or my predictor variable, from which data set. So this part is always the same, data equals to, and then after that, you put the name of your data frame. In this case, my data frame was named data, so that's why you were saying data equals data. Then you use the model.fit to basically get and estimate the parameters that you want. Because we are using an external package, we do not need to bother and go and calculate alpha and beta ourselves. That fit function does that for us. In fact, after running that, if you go with model.params, you will get the value for intercept and the value for time, which is basically the slope. And they are identical to the values that we calculated, which is cross-check. In the notation that we've been using, alpha is the intercept and beta is the slope. Our alpha was calculated to be -16 blah blah blah, and beta was calculated to be 11.977. And we can go ahead and use this to basically predict our y values based on our x values. So that will use the intercept and the slope that it calculated. It creates the linear equation. It feeds all the x values, gets all the y values, and put them in the object that I'm calling a speed underline pred. And when I plot that against my initial historical samples, I will get a plot very similar to what we received from our primitive Python code. Does that make sense?
Yes.
Yes.
So if it was your call, would you rather use the primitive Python or the package?
Definitely the package.
Probably the package. Usually that's more straightforward, but I think it is valuable that you know how to make those calculations in primitive Python as well. Ilyana, if you like primitive, that is all right. I know people who don't like to use packages for things that they can do in a more transparent way. That is really your call as the person who is writing the code. I have a question here for you. How good do you feel about this predictive model? If you were about to make a decision based on this, do you feel comfortable? Do you feel certain? Do you feel that you can trust it?
No.
Not at all. So, if you had no other models, would you rather not use this one also? If it was the only choice, then you guess. If I had no other use, okay. So that is a very important thing to know. There is this famous quotation, I'm not sure who said it, but every day of my PhD life, I have come across that. All models are wrong. Some are useful. So even though this looks like a simple linear model to you, and I couldn't hear you, Dr. Cleveland, if you said. I don't know if it's just me, but your voice is not coming through.
I'm plugged in. Richard Feynman, I think, is the source of that quote.
Oh, cool. So you may think that if you use a very fancy, complicated model, you will always get the right answer. But unfortunately, that is not true. So the whole idea about modeling is that we want to create a simplified enough version of the reality that can help us to make a decision. In this case, if you had no model, absolutely no model, you had no basis for making a decision. If you had only one model and this was it, then you could pass a judgment and you could say, okay, but judging by numerical and visual assessment, I would say that I'm not very certain about values between 4 and 7, but I feel better about values around 1 to 3. So as bad as this might be, you're still able to make a judgment. So this is not a completely useless model. You may not feel as comfortable as if you were with an exponential model or even a fancier one, but it's not completely garbage. Always keep that in mind. The level of certainty and uncertainty of a model really depends on your judgment. But you need to always keep in mind that the model may fail at certain ranges or under certain situations. And you need to report that as the person who has created the model. So we are at the end of our example 1. Do you have any questions? Do you have any points that you do not feel comfortable with? No? Yes?
Feeling comfortable.
Cool. Do I have only one person feeling comfortable with the entire thing? Okay, I'm good. Comfy. Okay. Now, let us move on to example 2. In example 2, we are working on a problem about advertising in cells. This is a classic regression problem. Actually, if you want to spend the time and look up different blogs on linear regression, you will see this example pop up more than a few times. The general idea is that we have made observations and a data set of how much a company has spent on TV advertising, radio advertising, and newspaper advertising, and then how many of a certain product they have sold. So we are interested in exploring the relationship between these parameters and answering the following questions. Can TV advertising spending predict the number of sales for the product? Can radio advertising spending do the same thing? Can newspaper advertising do the same thing? Can we use the 3 of them? So instead of using one predictor, can we use multiple predictor variables? And in that case, we are dealing with a multiple linear regression model. And then at the end, we want to know which parameter is a better predictor of the number of sales for the product. So you already have this CSV file, so you just need to read it. And looking at the first few rows, you will see one column for TV, one column for radio, one column for newspaper, and then one column for sales. These are how much we have spent, and these are how much we have sold. So we can actually go on and describe the data set and see that we have 200 records in our data set. We can have a look at the mean, the standard deviation, and the 5-number summary of these columns. So I'm defining 4 objects here. Another spelling mistake by me. Go ahead and fix this. This should be sales. One object for my TV column, one object for my radio column, one object for my newspaper column, and one object for my sales column. I'm getting the covariance and variance for my data frame. I will get a table like this. Do I have a volunteer who wants to unmute their mic and tell me what they can infer about the relationship between TV and sales based on what we are looking at?
They have a high positive correlation.
So what can you infer? What is your final verdict?
Like just looking at TV or compared to like radio?
Just looking at TV and sales.
A strong positive correlation.
You're saying a strong positive.
Yes.
Okay. Do I have any other ideas that would disagree with Ilyana? Do you dare disagree with Ilyana? Okay, so I need another volunteer to pass a judgment on radio and sales.
The correlation. All right, can you hear me?
Yes, way
Okay.
better now.
The correlation between radio and sales isn't as strong as TV and sales.
Okay, but is that all you can infer?
It's still pretty strong. It's a positive correlation.
Okay, thank you. Do I have anyone who wants to oppose that idea? No, okay. Another volunteer for newspaper and sales?
It's also a positive correlation, but it's kind of the weakest of the 3 of the.
Okay. Any Anyone has a different opinion? Ileana, now you're changing your answers and you're getting away from my wrath. So, all of you, you cannot look at covariance and pass a judgment on the strength of the relationship. Keep that in mind, because that is not normalized. You can look at covariance and say if it's a positive relationship or not. But because we are dealing with different variables in each case, you cannot really go ahead and compare them. You can do that by using the correlation coefficient, the table below. So looking at these, you can say, okay, newspaper, radio, and TV all have positive relationships with sales, but TV has a much more stronger relationship, and newspaper has the weakest relationship. This is the metric that you can use to pass judgments like that. On covariance, you can simply say if it's positive or negative. Are we good?
So
Yeah.
covariance is just positive or negative, and the correlation coefficient is how we determine how strong it is.
Yes, but the correlation coefficient also tells you about the positive and negative. So if you were to choose between covariance and correlation coefficient, definitely go with the second one.
Because it tells both, correct?
Yes, exactly.
Okay.
And as another reason, as the third reason, you can actually compare with correlation coefficient. Because it is normalized, you can go ahead and compare TV and sales with radio and sales and say, okay, TV is stronger. So, any other questions on this? Exactly, Dule. Any other questions?
Why is R squared usually used whenever you're doing like linear regressions? Versus
Actually,
because I feel like that's usually what you see on the graphs.
these are the three well-known methods of calculating correlation coefficient: Pearson, Kendall, and Spearman. As I said, if you want, there are several good blogs and videos on their differences, their underlying assumptions, and their applications, and actually the places where you should not use them. But Pearson's R is the most common because of the wide range of problems that you can apply to. So the reason behind its popularity is probably its simpler nature, it's easier to communicate, and it's kind of more relaxed on the assumptions.
Yes, so to answer your question, it's been used historically because it's easy to compute. And so people present it with their results as their demonstration that they've got a great linear fit. And that's why we're emphasizing that you always plot stuff. Because I don't know if Farang made it. We talked about, you can take a circle. We can make the blue dots fall into a circle. And they're clearly correlated, but nothing will work at that point. You can't fit anything. And you would never know that unless you plot the data.
Okay, thank you.
So any other questions? Cool. Moving on. We're going to answer the first question now. Can TV advertising spending predict the number of sales for the product? I'm going to use my stats model, sales and TV, from my DF data frame. The parameters are here. You do not really need them. And we are going to make a plot have our TV spendings on the x-axis and the sales on the y-axis. And it will be something like this. What do you think about this? A strong correlation. Okay, you already knew that. Positive 2, yes, you already knew that. Why can't we use primitive Python for a graph like this, Max? Why do you think that? Max? Rodriguez? I guess you're typing. Yes, but even in the primitive Python, you were not doing point by point. Even if it's 1,000 points, let me actually scroll up to where we were doing the primitive Python. So this was my code for primitive Python. Regardless of how many points I have in these arrays, this code will not change. So you don't have to do point by point, even in primitive Python. You would have to do point by point in primitive hand and paper, which you're not going to do. But with primitive Python, you still have the ability of using data frames and things like that. So going back to this graph, Braden, the line fits well. Actually, this is the best fit that you can get from TV and sales. So we for sure now know that there is no other red line that you can fit on this graph that fits better than this. But if you were to pass a decision, to make a decision based on this, what would you say? You're pretty confident? It certainly follows the general trend. TV ads are good to go. I would say it's all right. Okay, so if it was me, I would say that for the range of maybe up to 75, I am a little more certain about my outcome because these points are falling closer to my red line. But for very high amounts of TV advertising spending, I'm not as certain because sometimes it's way high, sometimes it's way low. So the guy comes to you, he asks, should I spend 250 on my TV advertising? You say, yes, go ahead, you will make 25 cells. And then you will tell him to go ahead, you will make like 15 cells, and then he goes on and he sells less than 10. So you are not as certain about this part of the fit as you are with the initial parts. AJ, that is one way of looking at it, which is very realistic. There are many factors playing in. But my question was, if you look at this graph, these blue points and this red line, how can you pass a judgment? You can certainly say that this is capturing the trend, this seems like a good fit, but you need to be careful about the parts that you feel more certain and you find the fit more reliable than the others. That is probably a very wise decision to make based on this. So in the first half, you are more certain than the second half. You see the distances from red line is increasing as you move towards higher TV spendings. It is very important that you you cherish the things that you can infer from a plot. I'm going to do that for you. The word that Dr. Cleveland just typed is a hard word to pronounce, but it doesn't need to be a difficult concept to understand. Put simply, heteroscedasticity refers to the circumstance in which the variability of a variable is unequal across the range of values of a second variable that predicts it. So going back to our plot, you can say that in this range, let's say before 125, you have lower variability when you look at your sales with respect to your TV advertising spending, but you have higher variability as you move on. So that is an observation that you can make based on a plot like this. And you certainly want to consider that before passing a judgment or making a decision. Do we have a question? It does, Braden, of course. To be honest, if someone would come to me and would tell me that my TV advertising spending is the only factor impacting my number of sales, I would probably doubt their sanity. There are an ocean of different variables that may come in. Yeah. So moving on, we are going to answer the second question about radio advertising. Very similar method, only I'm changing everything from TV to radio. And now I get this. What do you think about this? Is it better? Is it worse? Is it more reliable? Which one would you like to go with?
It looks worse.
It looks worse. Why?
The points are further away from our line.
That is a good way of looking at it. It's very scattered. Any other ideas? You can actually say that it is not very consistent with the money spent, and that means that the relationship between these two variables, between your predictor and your output, is not as strong as with the previous case. Very good. Moving on, the third question. Left side behavior is clustered, but it still has outliers. Yes, correct, but it's more than the previous case, so it's even less certain. You're right. So the third question, newspaper, changing everything from radio to newspaper. We get this. How do you feel about this?
Lots of variance.
Bad.
You don't like it because, first of all, this line's slope is getting kind of low. Not a very good sign. It's not a strong relationship. Second of all, you are getting points that are very far from your red line all over the place. And that is not good news again. Braden, based on what we observed with the correlation coefficient, I wouldn't say that it's no correlation, but you can go ahead and say, yeah, it's a weak correlation. Okay. Now, for the fourth question, we wanted to know if we can use the three of them, TV spending, radio spending, newspaper spending, and make a judgment and make a linear model based on that. So this is a case of multiple linear regression. This is simply a linear regression model with more than one predictor. And it is modeled by an equation like this. So you still have your intercept as alpha, but you will have more than one beta. And the reason for that is that for each predictor variable, you're going to have a beta. Beta 1, beta 2, beta 3. Now, we are going to use the scikit-learn package another external package that you can use for linear regression to do this. First, I'm going to separate my predictors. I'm going to use my TV column, my radio column, my newspaper column as my x's. And then I'm going to use my sales column as my y. I'm initiating a linear regression model, and I'm fitting x and y. This is a different syntax. So you will first put in your predictors, and then you will put in your output. And when you get the parameters, how many intercepts you expect to get? How many intercepts do we have in this model?
1.
1. That is your alpha, and that is the value that you get here. How many slopes do you expect to get?
3.
3, because you have 3 predictors. So these are the 3 values that you will get as your betas, and then this is your interceptor alpha. Therefore, our model can be written as sales equal to 2.938, which is my alpha, plus my first beta multiplied by my TV, my second beta multiplied by my radio, and then my third beta multiplied by newspaper. We can predict sales from any combination of TV and radio and newspaper advertising costs. So at this point, if you come and tell me, I have spent this amount of money on my TV advertising, this amount of money on my newspaper advertising, this amount of money on my radio advertising, can you tell me an estimate of how many sales I will make on this product? I can use this linear equation to come up with a number. Is this plottable? It is plottable, but it's gonna be kind of weird, and we are not gonna get into that. And to be honest, after a certain number of variables, it will not be plottable. So my new x values, I have an example here. I have spent $300 in TV, $200 in radio, and $50 on newspaper advertising. And I want to make sure, or I want to use my 3 predictor estimate to see how many product I will sell. And the answer for that will be 54. So based on this, I would tell you, you will sell around 54 products. Now, the last question. Now that we have covered the first 4 parts, which parameter is a better predictor of the number of sales for the product?
TV.
I heard 1 TV, TVC, TV, all of them. Go on. I feel like I'm teaching 5 students, and I have 51 participants in the meeting. So either start participating or I'm going to call out your names. TV. Okay. So I'm getting more votes for TV, and thank you for the ones that have started participating. Please keep on playing with us. Why do you think that? Why did you make that decision?
It has the strongest correlation for the most amount of time.
So you're making that judgment based on correlation coefficients?
I guess.
Yes.
In addition to like the correlation coefficient, the graphs, it's kind of
The graphs, so visual assessment. What else? It's the one we have most confidence in. Rami, you could be a very good politician one day. So true, you have the most confidence in, but why? Based on the graphs, TV had the least scattered points. So again, visual assessment. That's for the American people to do. Yeah, that was wise. I want you to have a look at something. When we used 3 predictors in our multiple linear regression, we got 3 beta values. Do you think that looking at these 3 values can be helpful in deciding which one is a better predictor?
That'd be a yes.
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 But wait,
So
I'm not supposed to play.
what I wanted to point out at this point is that the only use of linear regression is not prediction. Sometimes we use linear regression because we are interested in learning more about how different variables are related to each other. So logically, before looking at these numbers, if I came to you and said, do you think the amount of money that I spend on advertising has something to do with my number of cells? Would you think that there was a relationship?
Yes.
So logically, we feel that there might be a relationship. And just for the sake of it, or maybe as part of a research process, we are interested to know which one of them has a heavier impact, which one of them has the least impact, which one of them is completely irrelevant. So that can be another application of regression models. Now, not today, but in our next lab, we will talk about numerical ways and metrics that you can use to actually say which line gives a better fit. But for now, what we talked about holds good. So visual assessment, correlation coefficient, whether our points are scattered, the variability around the red line, these are the things that you should always check. And that is something that makes plotting an important part of our analysis.
Can you reiterate the importance of betas? Like what we get from what we infer from the betas.
So basically, the beta is going to give you an idea about how heavy each predictor impacts the final outcome. So, for example, looking at these, you see that newspaper has a very, very low value that is kind of close to 0. So it doesn't have a big impact. Braden, based on this, yes, you can say that radio had a heavier impact among your 3 predictors. But simply looking at one of them alone will not necessarily give you a full picture. And that's what I'm trying to conclude at the end of the discussion. You have certain tools and you need to use all of them to get a more wholesome picture. So you're looking at visual assessments, you're looking at correlation coefficients, you're looking at multiple linear situations, and putting all of these pieces together will give you a better understanding of the situation. That was beautiful, Lee. Yes, look at the forest, not the tree. That was beautiful. So, at the end of this, I have given you a list of references for those of you who want to learn a little more. The first 3 are the ones that I actually used in putting together my lab notebook for today. And then these are some great reads that you can enjoy, some videos that you will probably enjoy more if you are into YouTube learning. You have one exercise in which you are going to use the cars df CSV files that they've given to you. In this data set, you have information about vehicles, including their age, their mileage, fuel economy, engine power, engine volume, selling price. And you are going to go through multiple steps and run analysis. In the first step, you are going to read the data set, explore the data frame, and in a markdown cell, briefly describe it in your own words. In step 2, you are going to calculate and compare the correlation coefficient of the selling price with all of the other parameters, except name, of course. And in a markdown cell, you're going to explain the result and state which parameter have the strongest and biggest relationship with selling price of the vehicle, very similar to what we did. On step 3, you're going to use linear regression modeling in primitive Python, so yay for you, Ileana, and visually assess the quality of the linear fit with age as the predictor and selling price as the outcome. So you want to know what will be a good fit with age on the x-axis and selling price on the y-axis, and explain the results of the analysis in a markdown cell. In step 4, you're going to use linear regression modeling with a stats model, so yay for the rest of you, and visually assess the quality of the linear fit with fuel economy as the predictor and selling price as the outcome. Again, explain the results of the analysis in a markdown cell. On the next step, you will do pretty much the same thing, but this time with the engine volume. Step 6, in a markdown cell, you are going to explain which of the 3 predictors in step 3, 4, and 5 was a better predictor or resulted in a better fit for selling price. On step 7, you're going to use a multiple linear regression model with scikit-learn and use all the parameters except for name, of course, to predict selling price. Then use this model to predict the selling price of a car that has the following characteristics and decide whether this prediction is reliable in your opinion. So that vehicle is going to be 2 years old, 17,000 kilometers on mileage, fuel economy measure of 224.2, and then engine power of 74, and engine volume of 1,260. And I have given you placeholders that you can use, even though after exam 2, I realized that giving you placeholders will give you more stress, which I was surprised to find out. So you can put your code in markdown cells however you want. And that's it for today. Happy November, everyone. Dr. Cleveland, I'm going to...
Election day.
Yeah, go vote. I'm not allowed to say anything else, but go vote.
Go vote. Yeah, we're not allowed to tell you who to vote for. Vote as much as you want. That's cute.
I'm going to pass the host back to Dr. Cleveland. Thank you, everyone. If you need a meeting with me right after this, send me an email and I will send you the Zoom link. Otherwise, be safe, take care, and we'll see you on Thursday.
All right, and let's see. I'm in 2 minutes or less. Let's go. Someone had asked about the projects. Here's the project directory that you will get to if you go by Blackboard. So there's 5 subdirectories in it right now: instrument calibration, image classification, DTMF, concrete strength, and classification. So I'm just picking classification as an example. So here's the current status of that project.
Dr. Cleveland, if we are supposed to see your screen, we can't.
Oh, yeah, that's the way to do sharing, because then you don't reveal anything. Let's try that. There we go.
Thank you.
So you get here through Blackboard. So here's one of the potential projects called genre classification. I don't know which of these. So this one is to look at a data set of different songs, and it has some various lyrics in it, and you can read that if that's something you might be interested in. It's going to be a classification project, so you're going to use a technique called K nearest neighbors, which I believe is in SkyPy, or you actually can Google search it. So that's one of the potential projects. That's obviously not quite ready to go. Next one is concrete strength, which is apparently empty. DTMF, I believe this one is reminding me why I dislike Microsoft products. There we go. Is a dual tone frequency decoder. So here's part of it, and that's the problem statement. It looks like there's a notebook started. Image classification is really just a problem statement. I don't think this one will get done this semester. The reason being is this particular library is big and it's designed for artificial neural networks, and we haven't even talked about that. So maybe a future semester. Instrument calibration, this one is almost ready to go. In fact, I had to sort some of the files and be sure that the solution wasn't there. This particular one has a bunch about instruments, but these equations might look a little familiar to you all. So this one totally uses the techniques that you've been shown today and a few that you'll be shown in the near future in order to be able to quantify the uncertainty of your fit. And the last project, let's see. So that's where the projects are. So you can expect these to actually have formal content in the next day or two. And we'll remind you on Thursday, that's the target date to have this stuff all ready to go. But you can take a brief look. Concrete strength is empty right this instant, but you've dealt with that in one of our earlier labs, and I'll get that loaded up there shortly. I'm surprised it's not there. So hopefully that will address your concerns on projects shortly. But these are group projects. You'll get in a group by Blackboard once the Blackboard grouping thing is turned on, and it has a way for you to pick, choose what group you want to be in. Once the group is full, you can't pick that group, and you would have to go to a different one. So with that, that's it for today. We'll see you Thursday. Have a great day. Be safe.
There was just one question. When are these due? That will be the last day of classes, or?
I intend for our sections to have them due on the scheduled final exam, which is not our third test. It's the actual final exam in the university schedule. So I think it's December 5th or 6th or something like that. We'll get that out to you. So you have at least a month. And they're all intended to be about the same level of workload. And the project isn't just a script. You've watched us make notebooks with animations and pretty pictures and citations in it. That's what we're looking for your end product as a team.
Yes.
Rame, we can't just use a sorting algorithm to randomly group us, so you don't have anxiety, because I don't know how Blackboard does that.
And besides, you having anxiety is the best part of the semester. So.
Yeah, I mean, the thing for you to do is if you have anxiety, wait a week and then pick a group, because there'll maybe only be one left. But that may not be the group you want to be in. Anyway, goodbye, everybody. Have a great day. And hopefully I'll get these uploaded one of these days. And we'll see you on Thursday. And take care. Bye-bye.
Bye.
Yep.